Hello, in this lecture we'll answer two questions. In the first question, we find out the area of this circle. In the second question, we find out the area of this trapezoid ABCD. So we'll start with the first question. In the domain we have a circle, and we have also the common standpoint point P. From this common standpoint point P, we have two tangents for this circle, tangent PA and tangent PB. In addition, we have the right angle ACP. This angle equals to 90 degrees. Side CP of the right angle ACP equals to 4 units in its length. This is line side BC that is equals to 1 unit in its length. Again, our mission is to find out the area of this circle. So first of all, we can implement here rule 2. So I can take here rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle, and this is the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why put in our drawing? We have the common standpoint point P. From this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So write it down. According to rule 2, PA equals to PB. But it is given as a question that PB in total is equal to 4 plus 1, that is 5. So PB equals to 5. And one here that PB equals to 5. And for this equation, PA equals to PB equals to 5, we derive that PA is also equal to 5 units in its length. PA equals to 5. And PA equals to 5. In the next step, I'll copy the right angle ACP in the new page and we'll implement the Pythagoras theorem in this right angle ACP. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. So actually, this is the right angle ACP that I come from the original drawing. According to the Pythagoras theorem, in this right angle ACP, AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. So I write it now. AP squared, that is the square of the hypotenuse, is equal to AC squared plus CP squared. AP equals to 5, therefore AP squared is 5 squared, that is 25, and it is equal to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, it is 16. So in total, I should find out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and you get that 25 from 16 is 9, so 9 equals to AC squared. Here we take a root out of this equation, and finally you get that AC, the missing side AC, is equal to the square root of 9, that is 3. So AC equals to 3 units in its length. This is answering AC that is equal to 4 units in its length. So here AC equals to 3 units. AC equals to 3. In the next step, we define the center of this circle. This point is point O. And we also define the radius of this circle as x. So in the next step, we join points O and B together by a straight line. OB is of course the radius of this circle, that is equals to x, according to our definition. So here we can implement rule 1, repeat rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have tangent AB that is tangent to this circle. Here at this point, point M. Point M is the point of tendency of tangent AB with this circle. And we also have the radius OM that is equals to R. The radius OM is drawn to point M that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Now in our drawing, we have the radius OB that equals to x. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever your radius is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent to the circle. So PB is a tangent, it is absolutely a straight line. So if we focus on the upper side of this straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side, the straight line PB, must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of PB at point C? We have this angle that is right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. So this missing angle must be equal to 90 degrees in its size. In the next step, we will do construction, that is to say, from point O, this is the center of this circle, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AC. This point is point E. By doing this construction, we can take quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle front a square. So we will make quadrilateral OECB is rectangle because it has 4 right angles. So write it down. Quadrilateral OECBC is rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OECB, side CB must be equal to the opposite side OE. But CB is 1, therefore OE must be also equal to 1. Likewise, according to the same rule, in the same rectangle OECB, side OB must be equal to the opposite side CE. but OB is x, therefore CE must be also equal to x. What is the length of the missing line segment AE? On the moment, it is very easy to see that AE equals to AC minus CC. Again, AC minus CC equals to AE. So I write it now. AE equals to AC minus EC. So AE equals to AC. AC is 3 minus EC. EC is x. So in total, AE equals to 3 minus x units in its length. A equals to 3 minus x. In the next step, we join points O and A together by straight line. OA is of course the radius of this circle, that is equal to x according to our definition. In the next step, I'll copy the right triangle OEA in a new page and we'll implement the Pythagoras theorem on this right triangle OAE. Here by PT is the evaluation for Pythagoras theorem. So this is the right triangle OAE, this is according to the original drawing, according to the Pythagoras theorem, in this right triangle OAE. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. So I write it down. OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. The hypotenuse OA equals to x units in its length, therefore OA squared is x squared. And it is equals to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared. Plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total, we should find out that x squared equals to 3 minus x squared plus 1. Here we'll open the brackets on this side of the equation and we get that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x, plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. After cancelled x squared, on this side of the equation we have with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we should find out that 0 equals to 10 minus 6x. Here we add 6x to this equation and we get that 6x is equal to 10. Here we divide this equation by 2 and finally we get that 6x over 2 is 3x is equal to 10 over 2 is 5. So in total we found out that 3x equals to 5. Here we divide this equation by 3 and finally we get that x equals to 5 over 3 units in its length. So we found out that the radius x of this circle is equal to 5 over 3 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So as you know, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. And the radius of our circle is x, therefore the radius squared is x squared. So in total, we found out that the radius of this circle is equal to pi times x squared. So it is pi, x is 5 over 3, therefore x squared is 5 over 3 squared. So in total, we found out that the area of this circle is equal to pi times 5 over 3 squared. So it is pi, and 5 over 3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area of this circle is equal to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equal to 8.727 square units. 8.727 square units. Okay, again, we should find out that the area of this circle is equal to either 25 pi over 9 square units, so in terms of numbers, the area of this circle is equal to 8.727 square units. So finish with the first question. In the next step, I will present to you the second question and you will solve it. In the second question, our mission is to find out the area of this trapezoid ABCD. It is given us the question that side AB equals to 16, side AD equals to 17, side BC equals to 25, and side DC of this trapezoid ABCD is equal to 44 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. Actually, we know that the area of any trapezoid is equal to the sum of its two parallel bases times the height over 2. And therefore, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases. The two parallel bases are AB and DC, and therefore the sum of the two parallel bases is AB plus DC times the height, that is h over 2. So write it down. If we found out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is actually with AB plus DC times the height h over 2. The height h must create 90 degrees with the two parallel bases AB and DC. So in order to find out the area of this trapezoid ABCD, we will do a construction, that is to say, from this point A, we will draw perpendicular on DC. So if this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We will define the touching point of the perpendicular from point A and DC. This point is point E. Likewise, we will define the length of this line segment DE as x. And we will also define the length of this line segment AE as h. AE is also the height of this trapezoid ABCD. Why AE is the height? Because of the fact that AE creates 90 degrees with the base DC. Therefore, h is also the height of trapezoid ABCD. So in the next step, I'll go with the right triangle ADE in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle ADE. Here, by PT is the relation for Pythagoras theorem. So actually, this is the right triangle ADE that according to the original drawing. According to the Pythagoras theorem, in this right triangle ADE, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. So I write it down. This will be equation 1. AD squared, it is the square of the hypotenuse, is equal to AE squared plus DE squared. The hypotenuse AD is equal to 17 units, therefore AD squared is 17 squared, that is 289, plus AE squared. AE is 8, therefore AE squared is 8 squared. Plus DE squared. DE is x, therefore DE squared is x squared. So in total I shall find out that according to equation 1, 8 squared plus x squared equals to 289. In the next step, we will do another construction. That is to say, from this point B, we will draw perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the tangent point of the perpendicular from point B in DC. This point is point F. So here, we know that ABCD is a trapezoid, and therefore side AB is parallel to side DC. So actually, those two angles are both located between the parallel lines AB and DC, and therefore they are defined as an interior angles. Okay. And those two angles are also both located on the right side of the straight line AE, and therefore they are also defined as one-sided angles. So in total, those two angles are defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So if it's quickly on rule 16, according to rule 16, the sum of one-sided interior angles is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B, and we have line I that cuts the two parallel lines A and B. So those two angles are both defined as one-sided interior angles, and therefore according to this rule, rule 16, the sum of those two angles is equal to 180 degrees. So angle 4 plus angle 5 is equal to 180 degrees according to this rule, rule 16. Likewise, those two angles are also defined as one-sided interior angles, and therefore the sum of those two angles is equal to 180 degrees according to this rule, rule 16. That is to say, angle 3 plus angle 6 is equal to 180 degrees. So we can actually implement rule 16 in our drawing. Because in our drawing, I only showed to you that those two angles are defined as one-sided interior angles, and therefore according to rule 16, the sum of those two one-sided interior angles is equal to 180 degrees. So this angle is the right angle, and the missing angle is the angle BAE. So the sum of those two angles is equal to 180 degrees according to rule 16. So I did not. This angle is the right angle, that is to say it is equal to 90 degrees in size, plus this missing angle, that is angle BAE. In total, it must be equal to 180 degrees according to rule 16. So again, according to rule 16, the angle that is the right angle plus the missing angle, that is BAE, in total, they must be equal to 180 degrees, while because of the fact that those two angles are both defined is one-sided integrals, and according to proof 16, the sum of those two, the sum of one-sided integrals is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get this. The missing angle BAE is equal to 180 degrees minus 90 degrees is 90 degrees. So if we found out that the size of the missing angle BAE, the size of this missing angle BAE is equal to 90 degrees. According to rule 16, of course. So inside quadrilateral ABFE, we have 1, 2, 3 antagons. The sum of 3 antagons is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ABEF, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle, if not a square. So we relate to quadrilateral ABEF is a rectangle because it has 4 right angles. So write it down. Quadrilateral ABEF is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle ABEF, side AB must be equal to the opposite side EF, but AB is 16, therefore EF must be also equal to 16 and it's in its length. Likewise, according to the same rule, in the sum of rectangle ABFE, side AE must be equal to the opposite side FB, but AE is 8, therefore FE must be also equal to 8 units in its length. What is the length of the missing 97 FC? From the normal, it is very easy to see that FC in total equals to DC minus DE minus EF. Again, FC equals to DC minus DE minus EF. So write it down. FC is equal to DC minus DE minus EF. So FC equals to DC, that is 44, minus DE, that is X, minus EF, that is 16. So in total, FC is equal to 44 minus 16 is 28, minus X. So FC equals to 28 minus X. In the next step, I'll copy the right triangle BFC in a new page and we'll implement the Pythagoras theorem on this right triangle, triangle BFC. Here by PT is a version of Pythagoras theorem. So for me, this is the right triangle BFC that is according to the original drawing. According to the Pythagoras theorem, in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. So I write it down. This will be equation 2. BC squared, that is the square of the hypotenuse, is equal to BF squared plus FC squared. BC equals to 25, therefore BC squared is 25 squared, that is 625, and it is equals to BF squared. BF is 8, therefore BF squared is 8 squared, plus FC squared. FC is 28 1 6, therefore FC squared is 28 1 6 squared. So in total, according to equation 2, we found out that 625 equals to 8 squared plus 28 1 6 squared. Here we'll open the brackets on this side of this equation, equation 2. And we get that according to equation 2, 625 equals to 8 squared plus 28 1 6 squared. 28 1 6 squared is equals to 28 squared, that is 874, plus x squared minus 2 times 28 1 6, that is 156x. So here we subtract 625 from this equation, equation 2, and we get that in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 8 squared plus x squared minus 56x, and 874 minus 625 equals to 159. So in total we found out that 0 equals to 8 squared plus x squared minus 56x plus 159. Here we add 56x to this equation, equation 2, and we get that here we have 0 plus 56x is 56x is equals to 8 squared plus x squared minus plus 154. According to equation 1, we have already found out that 8 squared plus x squared equals to 289. Therefore, we substitute we substitute x squared plus x squared in this equation 2 by 289. And we get that 56x is equal to 8 squared plus x squared is 289 plus 159. So we found out that 56x is equal to 289 plus 159. 289 plus 159 equals to 448. So in total we found out that according to equation 2, 56x equals to 448. Here we divide this equation by 56, and finally we get that x equals to 448 over 6. 448 over 56 equals to 8, so x equals to 8 units in its length. Our mission is to find out the area of this trapezoid ABCD. And according to equation 1, according to equation 1, we have only found out that x squared plus x squared equals to 289. We just right now found out that x equals to 8. If x equals to 8, it means that x squared equals to 64. So we can substitute x squared in this equation 1 by 64. We'll do it now, and we get that x squared plus x squared, that is 64, is equal to 289. So here we subtract 64 from this equation 1, and finally get that x squared equals to 289 or 64 is 225. So we found out that x squared equals to 225. Here we take a root out of this equation, and finally get that x equals to the square of 25, that is 15. So we found out that the height of this trapezoid ABCD, the height h equals to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. And I already showed you that The area of trapezoid ABCD is equal to the sum of its two opponent bases, that is actually AB plus DC times the height, that is H, over 2. So the area of trapezoid ABCD in total is equal to AB, that is 16, plus DC, that is 44, times the height H, that is 15, over 2. 16 plus 44 is 60, so this expression in total equals to 60 times 15 over 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. So in total, if we found out that the area of this trapezoid ABCD is equal to 450 square meters. So again, the area of trapezoid ABCD equals to 450 square meters. That is the answer to the question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this circle. So in the drawing we have a circle, and we have the common standpoint point P. From this common standpoint point P, we have two tangents to the circle, tangent PA and tangent PP. In addition, we have the right angle ACP. Side CP of the right angle ACP equals to 4 units in itself. This is the right angle, this is the side angle ACP equals to 90 degrees in size. This is 97 degrees, it is equal to 1 unit in its length. Again, our mission is to find out the area of this trapezoid ABCD, the area of this circle. Our mission is to find out the area of this circle. So here we can implement all two. Why? Because if you focus on this common standpoint point P, from this common standpoint point P, we have two tangents to the circle, tangent PA and tangent PP. According to all two, they are equal to each other. That is to say, PA equals to PB. And again, according to rule 2, PA equals to PB. But PB equals to 4 plus 1, that is 5. So again, PB in total equals to 4 plus 1, that is 5. So we can write here that PB equals to 5, and from this equation PA equals to PB equals to 5. So we derive that PA is also equal to 5 units in its length. So here PA equals, or PA or AP equals to 5 units in its length. In the step, I copied the right angle ACP in a new page and implemented the right angle. And implemented the Pythagoras theorem on this right angle, ACP. This is the right angle ACP that I got from the original drawing. According to the Pythagoras theorem, in this right angle ACP, AP squared, that is the square of the opponent, is equal to AC squared plus CP squared. Repeat again, AP squared equals to AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25, and this is equals to AC squared. AC is the missing side, so we leave it as it is. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation. And we found out that AC squared equals to 25 plus 16 is 9. So AC squared equals to 9. Here we took out of this equation and found out that the length of the missing side AC is square root of 9, that is 3. So AC equals to 4 units in its length. So here, this is the line segment AC, that is equals to 4 units in its length. In the next step, we define the center of this circle. This point is point O. We also define the radius of this circle as x. Then we join points O and B together by side line. OB is of course the radius of the circle that is equal to x according to our definition. So here we implemented rule 1. We have the radius OB that is 1 to point B, that is the point of tendency of tangent PB with this circle. Whenever your radius that is 1 to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. It is given us the question that PB is a tangent to this circle. So PB is a tangent, it is absolutely straight line. So if we focus on the upper side of this straight line PB at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that said that the sum of the angles on one side of the straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line PB at point C must be equal to 180 degrees. So which angles we have at the upper side of PB at point C? We have this angle that is right angle plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction. That is to say from this point O, we draw perpendicular on AC. So this angle also 90 degrees, and this angle also equals to 90 degrees according to our construction. And we find the tangent point of the perpendicular from point O and AC. This point is point E. By doing this construction, we created quadrilateral OECB. Inside quadrilateral OECB, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OECB, we have 4 angles. And according to rule 5, any quadrilateral that has 4 angles must be a tesseract angle, a quadrant square. So related to quadrilateral OECD is a rectangle because it has 4 angles. But we also know that the opposite sides of rectangle are equal to each other. So an rectangle OECD, side CB must be equal to the opposite side OE, but CB is 1, therefore OE must be also equal to 1. Likewise, according to the same rule, in the same rectangle OECB, side OB must be equal to the opposite side CE, but OB is x, therefore CE must be also equal to x. What is the length of the missing line 7AE? A equals to AC minus CC. Again, A equals to AC minus AC. So A equals to AC, that is 3, minus AC, that is x. So in total, A equals to 3 minus x units in its length. In the next step, I join points O and A together by side line. OA is of course the radius of this circle, that is equal to x according to our definition. In the next step, I copied the right green triangle OAE in the new page and we implemented the Pythagoras theorem. It's right green triangle OAE. Okay, this is the right green triangle OAE that I copied from the original domain. According to the Pythagoras theorem, this right triangle OAE, OA squared, that is the square of the hypotenuse, is equal to AE squared plus OE squared. Again, OA squared equals to AE squared plus OE squared. OA is x, therefore OE squared is x squared, and it is equals to AE squared. AE is 3 minus x, therefore AE squared is 3 minus x squared, plus OE squared. OE is 1, therefore OE squared is 1 squared, that is 1. So in total, we found out that x squared equals to 3 minus x squared plus 1. So here we open the brackets on this side of the equation and find out that x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared minus 2 times 3 times x, that is minus 6x plus 1. So here we have x squared on both sides of the equation, so x squared will get cancelled. So after cancelled x squared, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 6x. So in total we should find out that 0 equals to 10 minus 6x. Here we add 6x to this equation and finally found out that 6x equals to 10. So here we divided this equation by 2 and finally found out that 6x over 2 is 3x and 10 over 2 is 5. So 3x equals to 5. Here we divided this equation by 3 and finally found out that x equals to 5 over 2 and it's in its length. So if we found out that the radius x equals to 5 over 2 units. That is to say the radius x of this circle is equal to 5 over 2 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. And the radius of our circle is x. Therefore, the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 5 over 3, therefore x squared is 5 over 3 squared. So in total, we should find out the area of our circle is equal to pi times 5 over 3 squared. So it is pi, and 5 over 3 squared is 5 squared, that is 25, over 3 squared, that is 9. So in total, we should find out that the area of this circle is equal to either 25 pi over 9 squared. So in terms of numbers, the area of this circle is equal to 8.727 square meters. We finish with the first question. In the next step, I present to you the second question and we solve it. In the second question, our mission is to find out the area of this trapezoid ABCD. It is given us the question that side AB equals to 16 units, side AD equals to 17, side BC equals to 25, and side DC equals to 44 units in center. Again, our mission is to find out the area of this trapezoid ABCD. Actually, we know that the area of any trapezoid is equals to the sum of its two parallel bases times the height over 2. And therefore, the area of our trapezoid ABCD must be equal to AB plus DC, that is the sum of its two parallel bases, times the height h over 2. So then the area of our trapezoid ABCD is equal to the sum of its two parallel bases, that is AB plus DC, times the height, that is h, over 2. The height h must create 90 degrees with the two parallel bases AB and DC. So in order to find out the area of this trapezoid ABCD, we did the construction. That is to say, from this point A, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and DC, this point as point E. Likewise, define the length of this line segment DE as x. Also define the length of line segment AE as h. AE is also the height of trapezoid ABCD. Why AE is the height? Because it creates 90 degrees with the base DC. In the next step, I copied the right triangle ADE in a new page and implemented the Pythagoras theorem with this right triangle ADE. So this is the right triangle ADE that I copied from the original drawing. According to the Pythagoras theorem, this right triangle ADE, AD squared, that is the square of the hypotenuse, is equal to AE squared plus DE squared. Again, AD squared equals to AE squared plus DE squared. AD is 17, therefore AD squared is 17 squared, that is 289, and it is equal to AE squared. AE is h, therefore AE squared is h squared plus DE squared. DE is x, therefore DE squared is x squared. So in total, we shall find out that according to equation 1, 289 equals to h squared plus x squared. In the next step, we did another construction, that is to say, from this point B, we draw perpendicular on DC. So this angle also equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B in DC. This point is point F. So here we know that AB is parallel to DC, and those two angles, they are both located between the parallel lines AB and DC, and therefore they are defined as interior angles. In addition, those two angles, they are both located on the right side of the straight line AE, and therefore they are defined as one-sided angles. So in total, those two angles, they are both defined as one-sided interior angles. And according to rule 16, the sum of two one-sided interior angles is equal to 180 degrees. So the missing angle that is, this is the missing angle that is angle BAE plus this angle that is the right angle according to our construction. The sum of those two angles in total must be equal to 180 degrees according to rule 16. So repeat again. The right angle plus the missing angle BAE in total must be equal to 180 degrees because of the fact that those two angles, they are both defined as one-sided interangles. They are both defined as one-sided interangles, and according to rule 16, the sum of two one-sided interangles is equal to 180 degrees. So 90 degrees plus the angle BAE equals to 180 degrees according to rule 16. Here we subtracted 90 degrees from this equation, and finally found out that the missing angle BAE equals to 180 degrees minus 90 degrees is 90 degrees. So this is the missing angle BAE. This is the missing angle BAE. Again, this is the missing angle BAE. It equals to 90 degrees in its size. So inside quadrangle ABFE we have 1, 2, 3 angles. This angle equals to 90 degrees according to rule 16. This angle equals to 90 degrees according to construction, and this angle also equals to 90 degrees according to construction. So in total in quadrangle BAEF we have 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside the quadrangle ABFE we have 4 angles, and according to rule 16, according to rule 5, any quadrangle that has 4 angles must meet this rectangle if not a square. So we have to quadrangle ABFE is a rectangle because it has 4 rectangles. But we also know that the opposite sides of rectangle are equal to each other. So rectangle ABFE, side AB must be equal to the opposite side FE. But AB is 16, therefore FE must be also equal to 16 and it's in its length. Likewise, according to the same rule, in the same rectangle ABFE, side AE must be equal to the opposite side BF. But AE is edge, therefore BF must be also equal to edge units in its length. What is the length of the missing line? What is the length of the missing line segment FC? From the drawing, it is very easy to see that FC in total equals to DC minus DE minus CF. Again, FC in total equals to DC minus DE minus CF. So FC equals to DC that is 44 minus DE that is X minus EF that is 16. So in total FC equals to 44 minus X minus 16. 44 minus 16 is 28, so in total this expression equals to 28 minus X. That is to say the length of this line segment FC is 28 minus X units. In the next step I copy the right triangle BFC in a new page and we implemented the Pythagoras theorem on this right triangle BFC. So actually this is the right triangle BFC that I copied from the original drawing. According to the Pythagoras theorem in this right triangle BFC, BC squared, that is the square of the hypotenuse, is equals to BF squared plus FC squared. BF is 25, therefore BC is 25, therefore BC squared is 25 squared, that is 625, and this is equal to BF squared. BF is S, therefore BF squared is S squared, plus FC squared. FC is 28 minus X, therefore FC squared is 28 minus X squared. So in total we can find out that according to equation 2, 625 equals to H squared plus 28 minus X squared. In the next step, we open the bracket of this expression 28 minus X squared, and we can find out that in total according to this equation 2, 625 equals to H squared, and 28 minus X squared equals to 28 squared, that is 874, plus X squared, minus 2 times 28 times X, that is minus 56X. So here we subtracted 625 from this equation 2. So in this side of the equation we have nothing, that is to say 0. On the other side of the equation we have H squared plus X squared minus 56X, and 874 minus 625 equals to 159. So in total we can find out that the equation 2, 0 equals to H squared plus X squared minus 56X plus 159. Here we added 56X to this equation and trying to find out that 56X equals to H squared plus X squared plus 159. According to equation 1, H squared plus X squared equals to 289. So we substituted H squared plus X squared by 289 and found out actually that 56x equals to x squared plus x squared 289 plus 159. So in total we found out that 56x equals to 289 plus 159. 289 plus 159 is equal to 448. So in total we found out that 56x equals to 448. Here we divided the equation 2 by 56 and found out that x equals to 448 over 56. 448 over 56 is 8. So we found out that x equals to 8 units in its name. According to equation 1, we already found out that x squared plus x squared equals to 289. We just right now found out that x equals to 8. If x equals to 8, it means that x squared equals to 8 squared, that is 64. Therefore, we can substitute x squared in this equation 1 by 64. We did it, and actually found out that x squared plus x squared, that is 64, is equals to 289. Here we subtracted 64 from this equation 1, and found out that x squared equals to 289 minus 64 is 225. So x squared equals to 225 according to equation 1. Here we took a root out of this equation and found out that h equals to the square root of 225, that is 15. So we found out that h equals to 15 units in its length. That is to say, the height of this trapezoid ABCD, the height h is equal to 15 units in its length. Our mission is to find out the area of this trapezoid ABCD. And the area of trapezoid ABCD equals to the sum of its two parallel bases, that is AB plus DC, times the height, that is h over 2. Repeat again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is AB plus DC, times the height, that is h over 2. AB 16, DC is 44, h is 15, divided by 2. 16 plus 44 is 60, times 15 divided by 2. 60 over 2 is 30, so in total this expression equals to 30 times 15. 30 times 15 is 450. So in total we found out the area that we are looking for, that is the area of this trapezoid ABCD, is equal to 450 square units. Okay, thank you very much.